Yesterday we looked at type 1, that's where you reject HO when it was true. Type 2, that's where you accept HO when it was false. The first one is based on alpha, whatever alpha you pick, because that's the only region of the curve where you actually are rejecting, and if that's the only place you're rejecting, that's the only place you can make a mistake doing it. Type 2 error, which is we saw was typically worse than a type 1 error as far as the consequences. That carries with it a probability of beta, and beta is a kind of nebulous thing. It doesn't have an exact value. It's based on, well, we'll see. Let's just go for it. All right, so remember two ways that we can make mistakes in hypothesis testing. And by making mistake, I'm not saying that you wrote it up wrong or your results are wrong or anything like that. It just means that the conclusions we draw are based on weird samples, which are possible to happen. So if your null hypothesis is true and we mistakenly reject it, that's one mistake. If the null hypothesis is false, but we fail to reject it or we accept it, that's another mistake. Type 1, type 2 errors. All right. The way to remember, is we always start the hypothesis by assuming HO is valid. So rejecting it when we shouldn't is the first mistake we can make. Yeah, that's one way to remember it. All right, we talked about this. I'm not going to spend a whole lot of time on it. But remember, we always have a presumption of innocence for a defendant. That's HO is that they're innocent. HA is that they're guilty. Rejecting or failing to reject. If a defendant is innocent, HO, and we don't reject that, that's correct. If a defendant is guilty and we fail to reject it, then if a defendant is guilty and we fail to reject it, that's here. That is a type 2 error. All right. The other two are correct. All right. A defendant is guilty. We reject HO. That's right. We thought they were guilty. They turned out to be guilty. Everything is good. All right. If a defendant is innocent and we do not reject HO that they're innocent, that is correct. All right, you remember that. All right, this is the same thing, putting the letters on here. Remember a type 1 error? That's where you reject HO when it's true. That carries a probability of alpha, which you get to pick, 0.05, 0.01, 0.1, 0.01, whatever. If it's true and we don't reject it, then that's accurate. If it's false and we accept it, that's a type 2 error, and that carries with it a probability of beta. And if it's HO is false and we reject it, that's what we're supposed to do. All right, that has a probability of 1 minus beta, which we would call the power of your test, because the whole point in doing hypothesis testing is to be able to identify a false HO that we would subsequently reject. All right, so again, a type 1 error occurs if we reject HO when in fact it's true. In this case, we just had a bad pull. When we pulled the sample that we had, it was bad luck. We drew an unusual sample and we used that, we got a p-value that was really small. We used that to compare to alpha. It turned out to be less, when in fact it was, it's probably, if alpha was 0.05, it was one of the 20 samples that would be weird, right? And we just had bad luck and picked it. All right, so when you set your significance level alpha, you're setting the probability of a type 1 error, because that's your rejection region, the only place you can reject HO and make a mistake doing it. So the probability of a type 1 error is alpha. All right, when HO is false in reality and we reject it, that's what we're supposed to do. That's the right thing. This is the power of the test. We want that power to be high. Okay, a type 2 error. When HO isn't true, but we just don't reject it. When it's false and we accept it, we have made a type 2 error. To that we assign the probability of beta. Usually a type 2 error is worse. All right, here's another example. Let's just say you're running a power plant, and you know the temperature inside the power plant, you know, the actual machinery can only be at a certain degree level. Any hotter, then you've got a big problem. Things can go critical, machinery can break, lots of bad things can happen, right? So you get an alarm that says, well, HO is that the temperature is fine. HA is that it's too hot. You get an alarm and it says things are too hot. And you freak out and you shut the plant down and you start measuring things and checking dials and, you know, putting portable equipment into, you know, the works, you know, to check to see if the regular sensors are messed up, the whole bit. And you discover this was never too hot to begin with, right? So you rejected HO when it was true. That happens. Well, what's going to cost you in that case? A little bit of downtime, a little bit of manpower, a little bit of money. Better to err on the side of caution, right? But what if you that thing is humming along and you think things are fine, but it's going critical, right? Well, that's where you're accepting HO, that everything is fine, when in fact it's not, right? So you're going to sit behind your desk eating donuts and reading comics like Homer Simpson, and things are just going critical and you're letting it happen. This is kind of a hallmark of a type 2 error. Bad things are going on, nothing is happening to address them, right? A type 1 error, you think bad things are going on, you address them, you find out things are fine, and yeah, it's not good, but not addressing a bad situation is typically worse. All right, there is no single value for beta. We compute it based on a parameter value that's in HA. So let's just say HO is that P is 0.3 and HA is P is greater than 0.3. Then you can pick a P value for HA that's 0.4 or 0.5 or 0.35, anything within that range of alternatives to use to calculate for beta. And it involves two curves. So let's just kind of hold off until we get to the curves, and maybe I can make some sense of it for you. Now, this is important. There is a relationship that exists between alpha and beta. If you reduce alpha, right, if you decide, type 1 error at 0.05, 1 out of 20, that's a little bit high, and you start going for an alpha of 0.01, which is just one word sample out of 1,000, right? Well, that sounds great. You know, lessen the probability of rejecting HO when it's true. But what happens is you increase the probability of a type 2 error. So there's this balance that you have to run. So likewise, if you choose to increase alpha, you will decrease beta. This may be a good idea, right? Because if the consequence of a type 2 error is that extreme, you might want to err on the side of 0.1 for alpha, risk a bigger type 1 error than if you went with 0.5 and increased your beta and, you know, raised the probability of something bad happening. So it's a little bit of a dance, a little bit of a juggle. If you can reduce beta, and there are ways to do it, you subsequently increase the power of your test. That's where HO is false and you reject it, which is the whole point in the test. So big power is a good thing. All right, so the power of a test is the probability that the test correctly rejects a false null hypothesis. HO's false, yep, it's out, we rejected it. It's the complement of a type 2 error. So it's 1 minus beta equals power. Yeah. So if you get a small beta, you subtract a smaller value from 1, you increase your power, the probability of, you know, correctly rejecting HO. So to reduce beta, here's your 3 options, and you need to know these. You can increase alpha. We already talked about that. You got to risk that type 1 error, so you got to figure out what's a good balance. But if you increase alpha, beta goes down. You can increase your sample size. What happens in your sample size is the curves that you're in get taller and skinnier, and so the tails where all this error takes place shrink. So alpha you can't do much with because it's a set value that you pick, but beta can certainly shrink. It can shrink down, and that's a big help. Increasing your sample size makes everything more accurate. All right, as far as that alternative we talked about earlier, you can pick a value that's farther away from your HO value. All right, that is a little bit of a finagle, but it's the third option. Yeah, you don't want to just change, your alternatives just to make yourself look better. And again, you probably don't even understand what I'm talking about by that, but when we get to the curves, hopefully that will make sense. Any reduction in beta increases the power of your test. Okay, all right, here is, suppose your null hypothesis is true, all right? Suppose your null hypothesis is not true, all right? This would represent your HO value, and this is the world that you think you're in, right? This is some kind of alternative to it. It just happens to be arbitrarily placed a little bit to the right of the world you think you're in, all right? And if for some reason you should be rejecting HO, right? You should be rejecting this P naught value, then picture these curves overlapping so that this axis is over top of this one, so it's the same axis. Then this red part would poke into the part you're failing to reject, that you're accepting, right? So this is the part in the second curve that you should be rejecting in the first curve, right? So that's type 2 error. It's the other side of alpha. Other side of alpha. The other side in this curve is your power. All right, so if this red area gets smaller, then this blue area gets bigger. So that's the geometry behind it. All right, here they are together. All right, how beta interacts with alpha. As alpha decreases, beta increases. Okay, so let's just say this is the world you think you're in. This is the world that you're actually in, right? This is based on some alternative. This yellow represents things that you're accepting in the first curve that you should be rejecting, right? And it's the other side of your alpha, which is 0.05. Let's just say you change that 0.05 to 0.01, which would move this line over to here. Well, what happens is smaller alpha, but see how that yellow region is bigger? That is your type 2 error. That's your beta. And so if you pick a smaller alpha, you increase beta. The power here, I don't know, it's fairly respectable. It's much less respectable here, okay? So you could pick a bigger alpha, move that line over so you have more red, but that would give you less yellow. So there's got to be a sweet spot. It's kind of up to you what you think it should be. Okay. This is the same figure as this. The only difference is they increase the sample size. All right, alpha can't really change. I mean, it's just whatever you pick it to be. But both curves get taller and skinnier. So since beta, this is the part from this curve that pokes into the acceptance region in this curve where you should be rejecting, yeah, this basically is going to get smaller as your curve gets taller and skinnier. So bigger sample sizes, in my way of thinking, is perhaps the best way to decrease your probability of a type 2 error, make this red region smaller. And again, if you picture these two things overlapping like what we had previous, then as you raise your sample size, this is going to get smaller and smaller just because the tails collapse as this gets taller and skinnier. So a big sample size is a good way to increase your power and decrease your probability of a type 2 error. Alpha is alpha. Can't do much about that, okay, except you get to pick it. All right, so just to see that, do you see how much error you have here when you have smaller sample sizes? Smaller sample sizes are taller and fatter, but bigger sample sizes, they're shorter and fatter. bigger sample sizes makes your curves taller and skinnier, right? And so there's less area in the tails. So compare this type 2 error with this type 2 error, and it's only changing sample size. So power's bigger, big sample size, good way to go. All right. So really, these are all based on alternatives. Here's your original P naught. Here's your P alternative, right? And if these are close together, then they have more overlap. If you pull them farther apart, you see alpha doesn't change, but beta does, because there's just less overlap. All right, there's less area to the left of alpha to create beta, which increases your power. But you know what? Picking alternatives just seems a little arbitrary. You know, I think your basic control over this is to, you know, play around with your alpha value, make it as big as you can stand it, or raise your sample size. But this will be the third of the three. Move your alternatives farther apart. Here they're pretty close. Here they're far apart. And basically, you know, your tests do distinguish from alternatives that are farther apart. They have trouble with alternatives that are closer together. Interesting. All right, so that's it. This is going to be up and posted. You do have an assignment. It's posted on the board, so you can go ahead and get started on it. And yeah, we are having a quiz tomorrow. It's over 2 proportion procedures, Z procedures, and it's got a little bit of this power. Really, you don't have to draw curves or anything, but you do need the concepts. You need to know what a type 1 error is, what a type 2 error is, you know, which is worse, you know, what the consequences would be given a scenario, and then you need the 3 things that we talked about, these 3 things right here, to reduce beta and increase your power, increase your alpha carefully, increase your sample size, right? Or pick an alternative that is farther away from your HO value. That's for your calculations. That's the one that I have the least respect for, is number 3. But those are your 3. You'll need to know all 3 of them.